good. I just jumped back in the presentation. I don't know where you started. I guess you didn't see anything from the beginning. I had this quote citing the IPCC report, and that it's not a crystal ball. And then I told you a little bit of this downscaling procedure that we have, the global climate models, which are downscaling into regional areas to get into the sea, to be able to look at the water quality and ecosystem changes in the end. And that is a lot of different steps here to get there. And we need to remember that's a lot of uncertainties within this. We have our RCO Scooby, which we need atmospheric forcing to, and the river flow, river loads. And then we can get out our output values. And we have, from the IPCC, we have 4 different RCPs. And they are used in the climate, global climate models, which have a coarse grid, which you can see on the figure to the right here. I hope you can see it at least now. And then this is downscaled with region coupled models, so atmospheric ocean models into a higher resolution covering also the ocean. But in this study, we have used 2 RCPs, 4.5 and 8.5, and 4 different global forcing, 4 different global models, giving us the atmospheric forcing to RCO Scooby. And these global models are also forcing the E-height model, which gave us the river loads and the nutrient loads, freshwater and nutrient load to our model. And I think I was here somewhere. And then in addition to this, so now we have the future atmospheric forcing, and we have the future river load forcing, but then we have also the human people acting and living, and so then we add to these 3 nutrient scenarios due to socioeconomic factors and also due to policy action. So what the politics will do with these. So we have 3 scenarios. We have the Baltic Sea action plan, where we are decreasing the nutrient loads. We have the reference scenario. It's actually we are keeping the nutrient load in that scenario, but it's since there will be climate effects such as more raining and higher river flow, we will also have an increase of nutrient load. And then we have the worst case scenario, which is increasing nutrient loads without reductions at all. So that is what we have to force our model, RCO Scooby. And then this is what we get out. This is model results. It's just an example. It's a primary production in the Baltic Sea. But what you can see is 4 global climate models that are forced with 2 different RCPs. And in addition to that, we have added 3 nutrient load scenarios. So it's a lot of runs and impossible to work with that amount of data to show the results. So therefore, we are discussing in terms of ensemble mean and the range between the different models or forcings in this case. And then it can look like this instead. And this is how the coming figures will look like, that we have these lines, which are the ensemble mean. And then we have a standard deviation, which are the colored area around the different lines. And the purple here is showing the worst case nutrient scenario, and the dark purple is then the highest or worst case emission scenario, so the RCP 8.5, while the lighter colors are RCP 4.5. And then they have the Baltic Sea action plan is blue. So then we have decreased the nutrient loads. And in between they have the yellow-orange, which is the reference nutrient load. And to start with the forcing or the nutrient load, it can look like this. So this is the nitrogen load with rivers, and we can see observation here as black dots to the left. And then in 2006 we start these climate scenarios, or this forcing with this from the climates, and we can see that the blue line is pretty much staying on the same level, and then it's decreasing about 2018, I think it is. It's decreasing a little bit more, but actually we are already almost at this Baltic Sea Action Plan level, and then we're keeping it at that maximum allowed nitrogen load. But for the worst case and the reference nutrient scenarios, we can see that it's increasing a little bit. And for phosphorus, we can see that we have a bit further to go before we are reaching the Baltic Sea Action Plan level of phosphorus load. And then we are keeping it at the, also here at the maximum level, while the phosphorus for the worst case and the reference scenarios are increasing a little bit more with time. What is interesting, I think, with these figures is that if you look at the nitrogen load that we had in the 80s, the beginning of 80s, we can see it's very high, and that we are not, as a mean average, we are not reaching this even in the end of this century. So even if you have this worst case scenarios, we have made a pretty good job so far with decreasing or reduce the nitrogen loads. And for phosphorus, it's even better. So I think that is a little bit optimistic looking at that way or that perspective. But still, there's a lot of nutrients, and we have a far way to go before we reach Baltic Sea Action Plan. And what does this mean when we have also the climate change? We start with the physical conditions and look at some results. This is the volume averaged Baltic Sea temperature, so entire Baltic Sea. Now we are in a project that is focusing on the northern Baltic Sea, but I don't have any specific figures for that, so you have to cope with this entire Baltic Sea figures. But here we can see that the temperature is increasing, and what we can see is also that for the two different RCPs, it's kind of the same increase until the mid-century, while it's and then it's a little bit going apart, so it's a higher temperature increase for the RCP 8.5. And the colored shaded area here in the different colors are the standard deviation. So the temperature is increasing, but for salinity, it's decreasing. However, we can see here that we have a larger standard deviation, especially for the RCP 4.5. But still there is a trend of decreasing salinity. But the uncertainty is a little bit higher. Looking at the oxygen or hypoxic areas in the Baltic Sea, we know that from observation that in 2018, in the fall, we had the highest extent or largest extent of hypoxic areas since 1962, I think. And when we look at the simulation or the projection of this, we can see that it will actually stay about this level throughout the entire century. If we are not reducing the nutrient loads, then the hypoxic area will decrease. This can also be seen in this way, where we have this historical period to the left here. It's kind of large extent of hypoxic area. Pink and red is oxygen lower than 0, thus no oxygen, while blue is low oxygen and green is better. And on the top row here, we have the RCP 4.5, and on the lower level we have 8.5. and from left to right, so we have the nutrient scenarios. So what we see is from the top row to the lower row, we have a warmer or temperature increase in the end of the century. But for the Baltic Sea Action Plan, we can see that it's actually not a big change at the hypoxic area. While if you increase the nutrient load in the reference and the worst case, we can see that the worst case is when we have a lot of nutrients and a warmer climate. So it gets worse both for nutrients, or the climate change are increasing the effects of high nutrient loads. That's what you could say. So now to my conclusions, that external nutrient loads are the main driver of oxygen depletion. And a future climate, it will amplify this oxygen depletion. So the impact of climate change is larger in case of higher nutrient loads. Thus, the implementation of Baltic Sea Action Plan is needed. It's very important, and it will significantly lead to improved marine ecosystems. But we also need to remember that the response of Baltic Sea is very, very slow. The Baltic Sea has high resonance times, and things happen slowly. And what maybe this fifth point here should have been on top, because it's most important. Of course, these are some substantial uncertainties in these future projections that I understand that I hope you understood from the beginning when you didn't see my slides. But in particular for salinity, we can see that is high standard deviation for the different forcings. I will just show you a quick slide. I hope I have time with that to show you how we can use these kind of models and how they have been used. So these climate scenario models for the physical parts are used in Climarine, for example, a project funded by Formas, which we have together with SWAM, and where we are working on the symphony model, including these climate projections, looking at the cumulative environment effects. And then we have the CIRRUS, a Horizon 2020 project, where we have delivered these data into another model, and we're doing together with DTU Aqua, looking at different species and how they're reacting to these climate changes. And then we also as boundary conditioning from, for example, Smart Sea and Clean Sea and a co-climb, for example. So thank you. Okay, so I got a question from Marco about why the trend of nitrogen and phosphorus is increasing. It's decreasing until today, but then increasing steadily until the end of the century, and in the reference and the worst case scenarios. And that is due to, I'm not sure really actually, but it's because within these increase of these nutrient scenarios, there's also the human activities. And in the reference scenario, for example, I can see if I can go back to that figure. The increase of nutrients are rather slow. I mean, it's not a big change, but it's due to higher participation of, it's raining a lot more, so there will be a higher runoff. And in the worst case, worst case scenario, we are also more people. So there's and we are not working as we should in the Baltic Sea plan. Okay, thank you.